equation was, the problem is my handwriting is not particularly nice. So I would have preferred that someone of you is writing it. One over one. So what do you think is the first step we are doing? Take the curl, but is it intelligent to take one step before to split this operator here into dv by dt, because then we know that we can switch here if we apply now the operator equals, and we put that vection on the other side. Okay, so now the trick that one has to dream, I guess, is that it's a good thing to split this using vector algebra. So if you look up in a textbook, maybe, do you know the Bronstein, something like this, some mathematical formula book. Then you can see this is the vorticity itself. Cross product with the velocity plus 1/2 gradient of the scalar product between vorticity and vorticity. This has one advantage because this is something that will drop out. So now we apply the rotation on this, and then of course this becomes d by dt of the vorticity. No, we don't call it vorticity. Yeah, relative vorticity. Okay, this is the relative vorticity. We can call it this way. Equals minus Nabla cross this term here. We keep this term for the time being. Minus 1 over minus Nabla 1 over rho cross gradient P minus 2 Nabla cross omega cross V minus, we just keep this term as it is always. And we have forgotten two terms, minus Nabla cross gradient of 1/2 V kinetic energy plus phi. So what happens to this term? The rotation of a gradient is 0. So this term is completely 0. This term becomes minus plus 1 over rho square gradient rho cross gradient pi. We simply work out this. So we are simply left with essentially, and we can, let me see. Yes, we can try to combine these two terms already. So we get that this is equal to minus nabla cross absolute vorticity, which here I simply abbreviated this cross V, where we have combined this term here with this term here. It's just the sum of these two into this. So eta is equal relative vorticity plus 2 omega, plus 2 omega. Okay, so that's this term here, plus 1 over rho square gradient rho cross gradient P minus nabla plus 1 over rho. This frictional term that we don't further discuss. Now a further trick is this double cross product here. We have to expand. So of course there's a simple rule, but this rule is even complicated because if this were just simple vectors, we could just use the rule. We take one out and then it's a scalar product of the other minus the other out and it's a scalar product of the other. But we also have to take into account that this is a differential operator. So we have to additionally use the product rule. So this term completely expanded becomes equal to taking out eta, the divergence of the velocity, plus v point gradient eta, product rho. We have to continue to apply the product rho here, minus v, the divergence of the vorticity, minus eta point gradient of the velocity. This term is 0. Because this is the relative vorticity and the rotation vector of the Earth is constant. Oh, its rotation is 0. Its divergence is 0. So, I think with this we are almost at the end. Because now we have d by dt equals the divergence plus v point gradient eta Oh, that was with a minus sign here. So that's a minus sign, that's a minus sign. Plus eta and gradient V. This plus the frictional term, minus, okay, minus plus 1 over rho square sinusoidal term and the frictional term. So this and this can be combined to the total derivative of the absolute vorticity, because the planetary vorticity vector doesn't change in time. So that's just the total derivative of the absolute vorticity. This is a term we need. Yeah, I think this was the equation we shown, right? Absolute vorticity, the divergence term is here. We lost the term. Oh yeah, this term here. Yeah, it's here. Okay. Yes, so the equation is correct. Only I have problems with the signs. This was the advection. This goes away. This is positive, yes, and this term is negative. Okay. This is the equation from the lecture note. So only essentially two tricks. We have to develop this term, and then we have to develop this term here. Two tricks, and then the solution is straightforward. And then to use the continuity equation here to simplify this equation further becomes clear, because the divergence can be replaced by the total derivative of the density using the continuity. And then these two terms can be combined for the absolute vorticity divided by the density, essentially. So that, I think that's straightforward.
First, I have a question.
Yes.
About the last term, the frictional term, how do we treat them?
Looks complicated.
Because if I mean, in the notes that I had got, it simply replaced the dynamic viscosity with the cinematic viscosity. So the curl of the density disappeared for the was constant. Even if maybe it was not carried out with these notes.
Because here now we have the...
Here we leave it as it is.
We simply leave it as it is, right? Yes. Okay, so the main application of the potential vorticity conservation is if the flow is adiabatic reversible. So we set the friction to 0. If we really should evaluate this term, then we have to specify what is this. In this case, it's the frictional tensor, or what are the frictional forces that we apply here. Right now, we don't care about that. We will actually specify this when we discuss the boundary layer processes. We will make some assumptions about what is important in the frictional forces, which components are important, and how we can express them not actually molecular friction, we believe, for our purposes, thinking on the large scale is never really important. It's then the action of the small scale eddies on the flow that we are interested in, that we want to parameterize as a frictional tensor or frictional forces. But right now, this term is there to be set to 0, because we also assume that the potential temperature, or the entropy, is a conserved quantity following the motion. Now this is a very, and the two go together, because adiabatic reversible motion then implies that also the potential vorticity is a conservation law. This is actually, you may sometimes think, we mix, if you mix quantities, you have to be very careful. You often assume if I mix something, this quantity is conserved and therefore it will mix to be like 0 gradient in the end. This assumption is usually based on quantities that are conserved if you mix them. But for the large scale motion, the only thing we can really assume to be conserved, even for adiabatic reversible fast motions, are the entropy or potential temperature, so that mixes, and potential vorticity. Not momentum, not any other. No, this is it would be very, we will come back to this problem later. If you try to mix momentum in the large scale flow, so you think you transport momentum by Rossby waves from the south to the north and mix it, it's not working because it's not a conserved quantity at all. Neither with temperature. You can mix potential temperature. Well, temperature, potential temperature become very similar if you just consider horizontal mixing, because they really deviate only if you include the vertical. But you have to, if you think of mixing quantities, we always have to consider conserved quantities. And the only conserved quantities we really have for large-scale dynamics, if we now consider for the time being the powerful assumption of adiabatic reversible motion, is the potential vorticity, also in its approximations, and is the potential temperature or entropy itself. These two quantities. There are no other quantities that are conserved following the motion of a particle. Globally, there are many more conserved quantities, of course. Momentum, angular momentum, they are all conserved, but not following a partial motion. So if we mix quantities, we have to be very careful to say, oh, this mixing will cause that the momentum is equalized. That's true in the small scales, but that's not true for the large scale. A large scale mixing of zonal momentum will not lead to a constant velocity. But you have to take into account this law if you want to know to what it leads to. It is much more complicated. The same with vertical mixing. If you think of the boundary layer mixing of course we know that we don't mix the temperature. If we mix very hard, what is conserved in the end? Okay, it's the potential temperature. So that if we mix in the boundary layer very hard by creating a lot of turbulence, the quantity that in the end is constant, the thermodynamic quantity, would be potential temperature or entropy. No stratification. That means that the stratification is neutral. That means that the temperature would actually decrease very much with height. We know that. So for this reason, such quantities are very important, and this is an exact conservation law. So this will also apply for any other planet, 100% sure, as long as we can assume, and this is actually, I think, any useful parameterization of processes is based on the assumption of adiabatic reversible motion. Because if you have to take into account the fact that entropy is created, that would complicate very much our treatment. So most of the convective quick processes are based on the assumption that, okay, so quick that heat exchanges can be ignored and we have adiabatic reversible motion. Otherwise it becomes more complicated, of course. Okay. I think these were the exercises, right? and they will become not more difficult but easier in the future. Is there a mistake?
I don't know. I'm just trying to see.
Okay, tell me, what is that?
Del U, del X plus del V, del Y, and the scale was 10 to the power minus 6.
So delta U by delta X.
Sorry, partial derivative.
Okay.
Yeah.
That should scale as 10 meter per second divided by 10 to the 6 meters. So that should scale as 10 to the minus 5 1 order second.
Yes, but in the notice 10 to the power minus 6.
Oh. Then there is a mistake.
Equation 9.
Oh, yes, okay. Yes, you're right. You're right, yeah. So this would be, so that is the divergence.
Yes.
du by dx plus dv by dy. And we said this is actually 10 to the minus 6 1 over second, even though we would have scaled it with 10 to the minus 5. The reason is that the flow is mainly geostrophic, and the divergence of the geostrophic wind is 0. Therefore, this just contains the ageostrophic component. So we will do this today actually. We could replace this by ageostrophic, because the divergence of the geostrophic wind, if we define it with a constant Coriolis parameter, is 0. Therefore, most part of this scaling actually drops systematically out. So they compensate each other. They cancel each other almost exactly. And so this is much smaller. It's actually very difficult this is a reason we will also see this in the lecture today. It is very difficult to take a wind measurement and to calculate its divergence. Because if you make a small mistake, the divergence you calculate may be very wrong, because it's mainly governed by the small ageostrophic component, whereas the wind that you measure is mainly the geostrophic wind. So if you make even a small measurement error and try to calculate the divergence, you may come up with a completely wrong distribution of divergences. Therefore, we have developed alternative ways of calculating the divergence, for example, and one will be in the exercises. So yeah, this is a good observation. This is a systematic cancellation, because the geostrophic component exactly drops out. Because you can see this, U would be, okay, minus over rho. Let's say we argue with F naught d psi d phi by d y, minus sign here, and V is 1 over F naught d phi by dx in our barotropic model, no? Then if you insert this here, the geostrophic wind here, you will see they exactly cancel out, give 0. That's the reason why this actually in reality becomes 1 order of magnitude smaller, because the geostrophic wind that dominates is canceling exactly out.
So yeah, if we take the flow to be incompressible, then the vertical scale over the vertical velocity scale over the scale gives us 10 to the minus 6, I think, based on the. So the divergence, fully divergent, three-dimensional divergence U.
This here?
If we say that it scales as vertical velocity over h.
Oh,
then
Yes, also, that's also true, of course. Of course. This will scale with dw by dz.
Yes.
And if you insert those numbers there, you get, that's right. And then you get to the 10 to the minus 6 also, given the vertical velocity. Because there we have inserted already, in the vertical velocity, we have inserted the number that we have measured or whatever. Yeah. So that it should be consistent, and it is consistent. Yes. So this should scale with dw in this case by dz, or w over the height of yeah. And then we get this consistent number, which is consistent with this. Yeah, everything should be consistent, and it is.
But then when you multiply by f, they tend to, I don't know.
Minus 6.
10 to the power minus 9, one says 10 to the power minus 10.
Okay. Let me just try to install this, and then. Yeah, it's good that we discuss this, because it's an important point, I think. Okay, so now we have this here, and you multiply this by f.
Yes.
So we have du a by dx plus dv a by dy times f, and that should scale as 10 to the minus 10.
A second square.
1 over second square. And so it's comparable in magnitude with the advection terms of absolute vorticity, which before there was nothing that could balance this term. So our conclusion would have been, okay, this is 0 or something like this. But now it can balance with the advection term, and so we know we have to take into account both.
But there's one saying is minus 9.
Yes, so we discarded that.
Okay.
So forget about that, that's wrong. That was a naive estimate.
Oh, okay.
Right, that was this naive estimate that we first made, and that was wrong. And then now we conclude, okay, it's not like that.
So the one here is the naive one, and then when you come down to equation 10, then it's...
That's correct. Okay, it was just a small twist to the thing. Sorry about that. Yes, so we will discuss all these concepts again today, so that's the good thing. You repeat this again. So, I want to see if this works. thought it worked before. Anyway, it doesn't matter. So today we will derive the basic set of equations in isobaric coordinates. I've explained already to you why this is done, because it simplifies the equation somewhat. It filters out already also some waves, particularly kind of sound waves, if we make this explicit assumption of the hydrostatic equation implicitly already. And for practical reasons, nearly or many climate models are posed in this pressure coordinate system or related pressure coordinate system. Now, it could be that instead of using the pressure P, many models use what is called sigma coordinate system, which is not the pressure, but is pressure divided by the surface pressure. And then this has the advantage that it varies between 0 and 1, essentially. But mixtures of the two also are used. But they all are based on this, on the fact that, you know, if we have our momentum equations, this is the horizontal Euler equation. We forget again frictional forces for the time being. We can add them later, but right now we forget about them. And so this is our horizontal Euler momentum equation, where we have neglected only frictional forces right now. And for the hydrostatic equation we have this. Just to make an estimate, because we have now numbers, how good this approximation is, and we discussed already, this doesn't mean that the vertical velocity is 0, because we can always derive what is the real vertical velocity, for example, by integrating the divergence equation or whatever, or any other equation. So the vertical velocity is not necessarily 0, it's just very small. And if you compare the smallness actually, so the term that we neglect, one of the terms that we neglect is the term rho dw by dt, right? That would be the advection term in the hydrostatic equation that we have neglected. So if we insert our scales, essentially this would be 1. Then we have, this is 10 to the minus 2 divided by 10 to the 5. So this scales like 10 to the minus 7, right? And these terms here, the easiest term we know that they balance each other. So this is probably a little bit more difficult to evaluate, but we could do it. But this is easy to evaluate. Density is again 1. G is about 10. So that's 10. And we compare that with a term that is 10 to the minus 7. So 8 orders of magnitude if we are really considering the large scales. We are quite safe with this approximation. It's not just is small. No, otherwise we wouldn't dare to pose numerical weather or climate models on this approximation. It has to be a very good approximation, and it is. Whenever we have such a relationship monotonically, because of course neither G nor the density changes. They change, but they don't change sign. Sorry, they change obviously. But whenever there is a monotonic relationship between, in this case, pressure and height, we can replace the z coordinate by this other coordinate. We could do the same if we have a monotonic relationship d potential temperature by dz equal to something. And this is done. If the atmosphere is stably stratified, then we can also use the potential temperature as a coordinate for our studies. no numerical model, as far as I know, is based on potential temperature, because this law, there are regions where sometimes it breaks down, and then your numerical simulation will go into deep trouble if these lines become very thin. So there could be a problem with that. But for theoretical considerations, it may be useful, or any other quantity. But the most commonly used is pressure or similar to pressure, like pressure over surface pressure, which is then called sigma, which gives us similar transformation relationship. The only thing we have to know is what we want to do. We want to express any field as a function now instead of a vertical coordinate of the pressure coordinate. And then that defines our transformation relationship. So now the derivative, keeping p constant, is equal to the derivative of the same field, keeping z constant, d psi by dz, dz by dx, but keeping p constant. And this is one of the transformation relationship. And then you may, for example, insert the pressure itself. The pressure gradient, keeping the pressure constant, is 0. Here is the horizontal, here would be the d by dx difference of the pressure. And here we get dp by dz. There we can insert our equation here. And dz by dx, keeping p constant. So that gives us, if we bring then one of the other side, that gives us how we can express our pressure gradient needed here, our horizontal pressure gradient. Our horizontal pressure gradient in the new coordinate system can be expressed as gradient, keeping the pressure constant, of the geopotential height, which is g times z in this case. So we can replace that immediately. So we are now talking about, and this will, when you come to current weather, we are looking at often at the geopotential height map of a fixed pressure level, and this fixed pressure level is 500 hectopascal. It's similar, actually, thank God, to looking at the pressure difference at 5 kilometers height. We know that more or less we are about there, but it's not exactly the same. So when we look on that map, on that, for example, ECMWF weather forecast map, we are looking at the height gradient in this coordinate system given the pressure level, which gives us very similar information to the pressure gradient on a height level, if we know about where the height level is. But we are usually speaking in these terms. And this is, knowing the geostrophic balance, we know that the flow, instead of in this coordinate system, is mainly along lines constant pressure. Here the flow is mainly along lines of constant height. So we can follow these lines. They are almost stream functions. Well, it's a stream function. But there are deviations from that if we consider the exact motion. So we can pose our momentum equation in this way, and this is done in all the models. For the hydrostatic equation, okay, we can simply reformulate this. This is, instead of dp by dz, is dz or dg times z by dp, and that is 1 over minus 1 over rho, which is also like what we call specific volume, right? And this is using the perfect gas law, R times temperature, absolute temperature divided by the pressure. So this can be, we alternatively used in the pressure coordinate system. Because now this is the dependent variable and P is the independent variable. So we can use this equation straight away. And here's just a coordinate that appears here. So this is our hydrostatic equation. And the good thing is for the total derivative, we have a very simple transformation law, and that means that is invariant. So if we apply the total derivative to a quantity that is now dependent on x, y, p, and t instead of z, we can simply apply our rule d by dt, dx by dt, d by dy by dt, but d by dp by dt. So now this total derivative gets a new, instead of w, d by dz, we get omega d by dp. And this omega is typically abbreviated as omega, is called vertical velocity in the pressure coordinate system, or pressure vertical velocity. And the important thing to note is, and also to be, that you can get confused, of course, is that if typically the vertical velocity is positive, the pressure vertical velocity is negative, because if we go up in height, the pressure decreases. We can easily show even a very good approximation, actually, of this is, so omega, the definition is dp by dt. And to a very good approximation, for most cases, this is w dp by dz. Just the vertical advection term. All the other terms, u, d by dx, d by dt partial, are much smaller than this vertical advection term because of the hydrostatic balance again here. So then this becomes minus rho gw. You see that gives us already, this is all positive, so when w is positive, omega is negative. And it also gives us an order of magnitude. So when we have this is 10 to the minus 2, then this will be 1 order of magnitude larger, the omega vertical velocity. Just as an order of magnitude, this can be used to translate between the two. We don't need it, but it gives us some idea. Now, to deal with the continuity equation, of course, you could transform this equation, the continuity equation. You could transform this operator and this operator. I think I've tried that, and this is probably even more complicated than the exercise that we didn't manage. So it can be done, of course it can be done, but you realize that the transformation of this term becomes quite complicated. But it will lead to the same result as the trick that we are using here now. The trick that is usually used is that we say, okay, to derive the continuity equation, we use the principle of mass conservation in the new coordinate system. So we express a mass element, delta m, or dm, as we usually do, density times volume. That's the definition of the density, no? The delta mass over delta volume is the definition of our density if the volume and the mass goes to very small, approaches zero. And then, of course, we know that this is rho times dx, dy, dz in Cartesian coordinates. Keep it simple. But we can replace this also, the dz now, with the hydrostatic equation. So that's 1 over rho dp, and we get the minus sign. Now we calculate the derivative of this. And you can work out that it's, if you calculate 1 over delta m d by dt delta m, so this is just exactly the same definition if you insert this mass element here. But now you have to use the product rho to evaluate these terms. So you take first out these and apply this to the delta x, and you get 1 over delta x, the other cancel out, delta d by dx, you exchange these two, and so on with each term. And you come to the conclusion that our continuity equation now looks like this, strangely. du by dx plus dv by dy plus dw by dt is equal to 0. And this equation is exact in the new coordinate system. If we assume that the hydrostatic equation is valid, then this is our new continuity equation. So it leads us to this equation here. It's interesting. We lose, in principle, in this new coordinate system, we lose a prognostic equation. It's replaced by a diagnostic equation. It's a major change in our systems of equations. Something is coming back in the end, because it turns out if you really want to pose a model here, you will have to carry an equation for the surface pressure. The surface pressure tendency equation. This you have to additionally use. It seems that in this system here, in the free atmosphere, it's not there. But if you apply at the lower boundary, you have to have an an additional equation for the surface pressure, which before you didn't have, because the surface height is prescribed, you know. But the surface pressure is not. You cannot just guess. You could make the assumption it's constant, but it's not. It's not exactly constant. So there comes an additional prognostic equation. So the number of prognostic equations in the end is the same. But it seems that here, that the continuity equation at least is diagnostic. And it looks like the equation that we have used already, that we have just used to evaluate the divergence. Right, the divergence-free condition in 3 dimensions would be du by dx plus dv by dy plus dw by dz is equal to 0. So our exact continuity equation in the pressure coordinate system looks exactly like our divergence-free equation, which is an approximation, of course, when we don't use the pressure coordinate system.
Excuse me, Professor, may I ask you a question?
Yes.
About the total derivative of equation 38. No, number 38, it's on the previous page. Yes. If you calculate the total derivative of P,
Yes.
we will get dP over dt plus dP over dt.
Well, dP over dt is simply treated as now as the vertical velocity in the new coordinate system. We forget that P is a dependent variable. We treat now P as an independent variable. So its total derivative is just the vertical velocity in the new coordinate system. So we have used this. You think we should have used here the product rule?
Yeah.
I was, it's confusing. I should have put it the other way around. This is not that d by dx applies to this, actually. It's that d by dx works on whatever comes behind here, like a psi or something like this. So it's not working on this. The typical definition of the total derivative. Yeah, I should have written this the other way around, actually. This d by dy is not working on this. It's not acting on it. This is the correct way to write it. So the other way around. Yeah, that may cause confusion. Now the thermodynamic equation. For a fluid, in its simplest case, we don't need a thermodynamic equation. But it turns out for a gas, we need to carry also a thermodynamic equation to close the system. There's an interaction between the fluid dynamics and the thermodynamics, very interesting interactions. Our heating in places can cause motions and so on. It's also true for the ocean, but for the ocean, it's a little bit less powerful than for the atmosphere, where it's the most powerful way to create motions. Most motions in the ocean are created by wind at the surface. There can be other ways, of course. But in the atmosphere, it's definitely the most powerful way of creating motion, is creating a temperature difference in two different regions. So the thermodynamic equation is very important. So it's convenient now. You can use any thermodynamic equation. You can use the equation for internal energy or for enthalpy. We have chosen here the equation for enthalpy. And the reason is immediately clear. So if you pose the first law of thermodynamics, we can call it, in terms of enthalpy, it reads Cp times the total derivative of temperature minus RT over P, so this is the specific volume, times dP by dt. And now we see what's the trick. Oh, here's the vertical velocity of the pressure coordinate system. We don't need to do anything here to evaluate this. We can just replace this by W. Equals, and now on the right hand side, in principle, is T times, in this formulation, T times the entropy change. Now, I'm sure you have done this in the people who have followed Adrian Tompkins' course, that you can replace at least the condensational processes by this expression here. And then you can try to work this out, how to combine this maybe with that here. So condensational processes can be expressed by this. So what, you remember what these symbols stand for? Maybe Adrian has used different symbols. What is MV? Is the mass fraction of water vapor or specific humidity. So that would be MV. We will come back to this later. MV would be called sometimes Q. No, we use Q. And that the definition would be the density of water vapor in a volume divided by the total density. The unit of this is unitless. And what is LV here? The latent heat of condensation. So that's a very big number. So that this process this is kind of pseudo-reversible. In principle, you can condensate and then you can evaporate it again. So you can include this in this equation here. But in our course, for the time being, we say, okay, we don't care very much what these processes are. We abbreviate them, all of the processes that may appear on the right-hand side here, which are then related, could be related to entropy production. If there's radiation processes in the friction processes in the boundary layer, and so on. We abbreviate all these processes by Q. That's it, Q. And then later we set it to 0 maybe. Because this is again the assumption, if this is 0, then you know temperature is not conserved. But which quantity would be conserved? Potential temperature. You could combine these two then to derive the potential temperature or entropy conservation again. And that would be the most powerful application of this equation again for fast processes. Not if we integrate long time, of course we have to specify this Q. Condensational heating, you know, is a very important process. And it is parameterized in models. But for some applications, it's useful to try to understand what is happening if we forget about these complicated processes and just think about our dynamical processes. We call them Q. And now the trick is, I told you already, that we can simply replace this by omega. And there are two terms, actually. And this is some very elegant coincidence, I think. There's the term omega dt by dp, and there's the term R. This is minus RT over P dP by dt. Sorry. So this is also equal to omega. So we combine these two. We can combine these two. This is omega times dt by dP minus RT over P. And you will show, and this is what we abbreviate this as a, oh, because we have a minus sign here, so we put this with a minus sign. And so this is 1 over, yeah, there's a CP, okay. We have to divide this by, if we just have this here, we have to divide this by CP to get this. But there's a nice coincidence that this can be expressed, these two terms can be combined to something that we may call a stability parameter, which can be just again expressed as a potential temperature change with our new height coordinate with pressure. So, and this will, it turns out for the large scale will always be positive. The potential temperature change with pressure is always negative, so that this becomes always positive. So this is the stability parameter. It's a very, very powerful equation. Later on we will assume, or that in the tropics there is actually a very good correspondence just between these two terms. Very powerful equation here, because we can say that any heating rate in our atmosphere is compensated by vertical motion. Sometimes we have to cool, when something is heated we have to cool off. There could be any processes to cool off, but it turns out it could be all of these terms in order to get into a stationary state, for example. That could be the horizontal advection term. But it turns out in the tropics often this equilibrium is very powerful. So any heating rate will be compensated by large-scale vertical motion. So in the regions where you have a lot of heating going on, convective regions, the consequence is that you have large-scale rising motion. In the regions where you have lack of convective heating, there will be no rising motion or even sinking motion. So this is an interesting equation. And so this will be also an exercise. Of course, we have used here the definition of potential temperature. And if you insert this potential temperature definition, you can work out that this is its derivative. And you can also, this is also an exercise, show that then that this is just comes back to your atmospheric physics course, that you can express the stability parameter as the difference between the dry adiabatic lapse rate and the actual lapse rate. In a stable atmosphere, this should be always positive. The dry adiabatic lapse rate, how much is that? 9.8 degrees per kilometer. And the real lapse rate may be something like 6 or 5 often. Anyway, this is in a stably stratified atmosphere, this is always positive. Oh, and we want to also transform our potential vorticity. And here again we see, so if we go back to equation 31, our potential vorticity that has taken the approximate form of just the vertical component, this one here. It is complicated even for an atmosphere. If we are incompressible, it's easier, but if we are really a compressible medium, it's this triple product of variables. But in the pressure coordinate system, we have the advantage that the density drops out again. So if we evaluate the derivative d theta by dz, we can evaluate this as d theta by dp, d theta by dz, inserting this, we get, and then dropping the g, because g is just a constant, we can redefine our potential vorticity in this pressure coordinate system as just the product of absolute vorticity, relative plus planetary, d theta by dp. So the interpretation now for compressible medium is very similar to that of what we had already for the incompressible medium, of course. slightly different. So for the incompressible medium, we had that eta over h, the height, should be a constant. Right? And now we have that eta d theta by dp should be a constant. Now we have used this to understand what happens if flow goes over a mountain, what happens to the, if this changes, then what happens to the relative vorticity, or to the, in this case, absolute vorticity. Now we can do the same actually with this equation. If we assume, and this is justified for this being constant, that if a flow is confined initially between two theta surfaces, so we can evade this approximately as d delta theta over delta p. If a flow is initially confined between two theta surfaces, and the flow is adiabatic reversible, so theta is conserved following the motion, then its delta theta should always be constant. But the p, if a flow goes over a mountain, the delta p may change. You can evaluate how much this is by knowing the height of the mountain and applying the hydrostatic equation. So our conclusion is again the same. No, this is constant, but if delta p changes, then the absolute vorticity should also change in the same way as we have applied this law here. Only that this is now really valid for a compressible flow. So we have to have this additional condition that we know it's adiabatic reversible for this process. That's a slightly more complicated interpretation of this. Now we want to look at some features of the extratropical flow. We don't want to read this. We want to look at some features. Okay, this is now, look at this is actually from a model verification web page. So I compare the performance of the general circulation model that I'm using with the observed data set, or what we call reanalysis data set, which is the closest we can get to any observed data set. So the second row here is actually the observed data set. And what we're looking here is at a zonal mean. So we integrate in the zonal direction. And so this goes from the South Pole to the North Pole. Here's the equator. And here is our new vertical scale. So consistently, we are now thinking in the pressure coordinate system. At the surface, we have high pressure, and then we go up. So this is our pressure coordinate system. About 1,000 hectopascal close to the surface. And then here we are at the tropopause, probably. Height. This is about 10 kilometers. And then we go further up. What is shown here is the temperature minus a reference temperature. This is sometimes done to highlight I could have shown the full temperature, but this is sometimes done to highlight the meridional changes here in temperature. So this reference temperature is typically just a function of the pressure, and is defined by an integral over x, y, and time of the total temperature. So we take a long history of our temperature and average that in the horizontal and in time direction, and then we get such a temperature, which is actually large compared to the deviations from that. You can see what is the absolute temperature value, about 300 Kelvin, 280 to 300 something Kelvin. But the deviations that we see here are in the order of 10. So most of our temperature is actually in this reference state, which is constant in the horizontal direction, but can vary in the vertical direction. So why this is done is because it may be explaining what we see here, and we've discussed this already. In the regions where we have strong meridianal temperature gradients, this is now for the boreal winter season, we get strong jets just in the region where we have the temperature changes, in the region of the tropopause, at 200 hectopascal. And we have much weaker jets in the summer hemisphere. See that? This goes up to 40 and this goes up to 25. Let's see if that's true for the opposite, for the boreal summer. Boreal summer is also true. We get the largest temperature gradients in the southern hemisphere, because the polar regions cool off very strongly and the equatorial regions, they stay relatively warm. And therefore we get strong jets. But in the northern hemisphere, the jets become much weaker. So we have indicated already that this may be explained by something that we call thermal wind equation. And it will be an exercise again for you to derive the thermal wind equation. All the interesting laws you have to derive yourself. So this can be explained by this equation here. Whenever we measure a meridional temperature change, then we expect a vertical change of flow. Not only zonal flow, but the same would be true if we have a d by dx change in the zonal direction of our temperature. We also expect vertical flow of the meridional flow, actually, vertical change of the meridional flow, and you will derive both laws. So this is a very powerful equation. It essentially it explains all jets. It doesn't mean that one is the reason for the other. So often we think for mid-latitude regions that this is the forcing and this is the response. The jet stream is the response to the imposed temperature difference. But this is just a diagnostic law. We cannot say. It could also be that in some occasions, this is the forcing, and this is the consequence. The truth is that this is a very, very good approximation. Always. You can take any jet, the African easterly jet, you will find it will obey this law. African easterly jet, the tropical easterly jet, all of these obey this law. So if you want to understand variations of these, you may alternatively, instead of looking at the wind, you may alternatively look at meridional temperature changes. This is a very powerful law.
Could you please elaborate more about the use of pressure and vertical distance? Because you say, like, for example, on the final session, you always look at pressure in equivalence to vertical depth, just like, for example, in the ocean. For example, if one uses the dynamical height, it's equivalent to the pressure in this bastion.
Yes.
But if you look at those plots, the pressure, which is in hectopascals, is way above the distance. But you say you look at it in, for example, in the sense that they are both equivalent.
Yes, you mean in these plots? In these plots, really, you could, yes, instead of, no, we could do this is done in the pressure coordinate system, therefore the pressure is used. But in order to understand what's on this here, on this scale here, we could again use the hydrostatic equation, integrate this, and evaluate what would be the equivalent height here, and we could come to a similar conclusion. So the height would be here, of course, 0, here around 5 kilometers, and here around 10 kilometers. So it's just, we have to get used to it actually, but all with the weather forecast that we look at, they are in this pressure coordinate system. So we better get used to that. But the interpretation is, yes, it's the same. We will look at this now. The interpretation is the same to look at the geopotential height map at a pressure level than looking at a pressure at a fixed height level, if these two more or less correspond. We can derive the same information from this, which is what we will do in a minute. So you will derive this equation, and of course you know where this equation comes from. It's the hydrostatic equation that has to be combined with the geostrophic equation. So U and V, we know how they vary, how they are related with in the geostrophic balance. Then we have to take a d by dp of that, taking into account the hydrostatic equation, and then we get to this law. Can also be done in the z coordinate system, but so speaking of the jets, we can have a look at the. So now we look at the height. Sorry, I always say height, but it's the pressure, again, the pressure level, which is here 200 hectopascal. So that's that's more than 10 kilometers. That's probably 12 kilometers height, where the jet is maximum. We have seen that in the previous plot. But now we look again at the time mean, but how it varies in the horizontal and directions. So also now we don't take a zonal mean, but we look, we see, okay, it's true that there is some kind of zonal symmetry, particularly in the southern hemisphere. But in the northern hemisphere, there are strong deviations from the zonal mean picture. It's not just one jet stream that is there, but there are variations. So we see the strongest jet stream, which is probably related to the strongest du by dp, and therefore to the strongest temperature gradients, are in this region here, are in this region here. Can you guess why? This is for winter. So in the winter season, we get probably the strongest temperature, regional temperature gradients along the coast of North America, and also along the coast of Asia in this case. You also note another thing, that we call this jet stream, no? This jet stream in the Atlantic is quite tilted, but the jet stream in the Pacific is quite zonal. It's an interesting asymmetry. The reason is actually quite complicated. People have written papers about this. Why is the jet stream tilted in the Atlantic and so straight in the Pacific? One possibility to tilt a jet is to have warming, land-sea contrast. So we have a strong warming here over the ocean and a cold continent, and that would tilt this jet. Other things that have been proposed and that work is actually the orography. The Rocky Mountains in combination with the Greenland orography will cause a stronger tilt of this jet. So both may work together. And in the Pacific region, okay, there's this mountain, and it causes waves also, the Himalaya, but it's further inland, so it's not really so close to the coast. We see another feature which is interesting. So what is this? So this is positive. That means the flow goes from west to east. Right? Westerly, what we call in meteorology, we call westerly winds. Okay? An ocean is the opposite or something. But you see here, there's something else. These winds are from the east to the west. What is this? Has a name. This is the tropical easterly jet. Easterly comes from the east. It's the tropical easterly jet, which shows up in the mean.
Is it part of the headless cell?
Yes, it's part of the headless cell. It's all of this is part of the headless cell. We will look at this later. It is part of the headless cell, yes.
But so, Professor, why is the jet stream stronger in the northern hemisphere than the south? Is it because there are continents arranged?
First, oh no, wait. This is winter, boreal winter. So temperature contrasts in the northern hemisphere are larger. Otherwise, it's probably the opposite. The mean jet in the southern hemisphere will be stronger because there are less perturbations from the continents. I think. I don't have an annual mean picture of this, but I think that's the case. But here it's clearly the case. This is a strong asymmetry because of the temperature gradients, and GJF are much weaker in the southern hemisphere. And okay, and now this is again. And now we are looking at something that we often look at current weather. This is the height of a pressure level. So again, think of it as the same meaning as the pressure at a height level. So if we want to understand the flow, we see the height is kind of low here and high there. That means the flow in the northern hemisphere goes along isolines, more or less in the geostrophic balance, along these isolines of constant height, as they would go along isolines of constant pressure. But here we are talking about height at a pressure level. And here we are looking at we are subtracting a zonal mean, so we want to see the perturbations of this. And we see that in the Atlantic there's this what we call ridge, in the Pacific there's this trough, and then we have a ridge trough and another ridge here. And most of these are really influenced by the mountains. We know already from potential vorticity conservation, the mountains have to do something to the flow when the flow is trying to get over it. And we will actually derive why there can be ridges and troughs over the mountain. There can be both actually. The solution of the forced Rossby waves that we will look at the next section, I think, the next lecture on Friday, we will show that there could be both. But depending on the wavelengths, and the wavelengths are such that there's a ridge here and there's a ridge also over the Himalayas. So we want to discuss a little bit further this quasi-geostrophic approximation that we know already quite well. I think I will go a little bit further. We started late. So we now use the set of equations and pressure coordinates that we have derived. From now on, essentially, we will use mostly that, but sometimes also we go back to the Z coordinate system. So the stability parameter will be just treated as a constant, essentially, for our treatment, to understand what's going on. So the idea is now to divide the flow into a geostrophic part and the ageostrophic part. If we define our geostrophic wind here as the k times gradient, this is now geopotential height, g times that, in our pressure coordinate system, and with a constant Coriolis parameter. So we think we fix our Coriolis parameter at some latitude. We don't go too far away from that latitude. Then this is of course the definition of the ageostrophic wind. If we can measure the total wind, we define the geostrophic wind, then this is the definition of the ageostrophic wind. But for the systems we are interested in, we also know already that the geostrophic wind is 1 order of magnitude larger than the ageostrophic wind. So the ratio of the two, ageostrophic versus geostrophic wind, is about 10 to the minus 1. That means that in many of our operators we can replace, for example, in the total derivative, is justified to replace the velocities by the geostrophic velocities. That means also we ignore the vertical derivative here. Turns out to be a good approximation. It's just the horizontal geostrophic derivatives. For the Coriolis parameter, we assume that we fix a latitude, and then we can treat some deviations from this, but not too large, so that we can expand our dependence on the latitude as a linear function of y. So we say, okay, this is f0 plus beta. The beta is the derivative of f with respect to y times y. So this is our Taylor series expansion of our Coriolis parameter at the latitude that we have fixed. And it turns out that also that this kind of means that we shouldn't go too far away. So our scale, our horizontal scales shouldn't be too large compared to the radius of the Earth in order for this term here to be small compared to this term here, which is one of the further assumptions of this beta plane approximation. So the radius of the Earth would be something like 6,000 kilometers, so we shouldn't go beyond 1,000 kilometers probably from this base point. Then the acceleration of our flow following geostrophic motion can be derived from the right-hand side of our momentum equation. So we want to evaluate what is this term here. Oh, I have to go to anyway, this is the right-hand side of our momentum equation. The only terms remaining for the time being for us are the Coriolis force and this pressure gradient force, the transformed pressure gradient force. And so we insert V is equal to Vg plus the A geostrophic part. F, we use our Taylor series expansion. And this we replace by the geostrophic balance. Then we see the largest term drops out. The largest term here is this times this times this minus this drops out. So the remaining are small deviations actually from the geostrophy in this equation here, which is one term is Fk cross the A geostrophic wind, and one is beta Yk times the geostrophic wind. There is a second order term also, which is beta K beta Yk times Va. We assume that is one order of magnitude smaller than any of these other terms here. So then our approximate horizontal momentum equation is this. And for the continuity, of course, we know our geostrophic wind is divergence free. So we have that the divergence of the A geostrophic wind is balanced by the vertical change of the vertical velocity in the pressure coordinate system. For the temperature equation, actually we make one further assumption which is related to what we have said here. We can express most of our temperature values by a vertical profile. We make it simple. We assume that we can divide our total temperature into a reference temperature that only depends on pressure, some kind of mean temperature, and a perturbation from that. And then we assume that the vertical change of this temperature is much larger than our temperature perturbation. This is an assumption that, however, often is valid. So the lapse rate is mainly explained by the mean temperature profile and not by perturbations from that. That's reasonable. If that's the case, our thermodynamic equation looks like this. And note that the vertical derivative here has not been cancelled out. We have just replaced the horizontal derivatives in the advection term by the geostrophic one. The vertical has been combined with this stability parameter, which in this case is just really just a parameter. So this becomes now a linear term because we express this sigma just as mean term quantities. And yeah, we can use these typical values for mid-latitude conditions, in mid-tropospheric conditions. This is now our full set of equations. Okay, the quasi-geostrophic vorticity equation, there's an exercise. You can derive directly from the quasi-geostrophic momentum equation, exactly, and you will get to this equation here. And this actually is an equation that we know already. This looks exactly like the vorticity equation that we have derived already. The vorticity can be generated by dilution or concentration of vorticity by this divergence term, and the advection of planetary vorticity. We can replace this term by the omega by dp and get to this version here. Now we have discussed that for many flows where we are without orography, to some extent a good approximation is the conservation of absolute vorticity to a first order approximation. So we may consider what is the case if this term is small for the time being. Then we have remaining these two terms. Advection of relative vorticity. What can change the relative vorticity? Advection of relative vorticity and advection of planetary vorticity. And this is quite interesting because if we look at typically at a geopotential height map at say 500 hectopascal, the flow goes around this. We have positive vorticity here and negative vorticity here. The flow does this, so positive vorticity, negative vorticity. This would be a line of constant geopotential height, which gives us a stream function, so the flow will flow around that. And now we want to evaluate, so what is, for example, going on if we are in this position here. So the advection of relative vorticity would make the vorticity tendency here, delta vorticity, would be positive, because this would be advected over there. On the other hand, the planetary vorticity advection means that we are advecting kind of in this direction less vorticity from lower latitudes. So the planetary vorticity advection would be negative. So there's a tendency for these two processes to cancel each other. And what actually happens, which term wins, depends on the wavelength. It turns out that this term wins for large wave numbers because there are more higher order derivatives here. So large wave numbers, that means small cyclones or anticyclones, will be mainly transported by the mean flow. They will just flow in the westerly winds and be all carried over. Whereas large waves, small wave numbers, may be either stationary or maybe even propagate into that direction. It's interesting. We actually could look at what is happening right now. I think it could be a good idea. it's too complicated, or we see something here. Okay. Okay. So whoever came to current weather knows this product Windy, which is essentially taking the ECMWF weather forecast and putting it in a nice format. And this is actually the geopotential height of pressure. I'm not 100% sure which button I click, but it essentially telling us the same things. I just will play this, and then we see what's happening. So, you know, we can interpret this as being Rossby waves right now. This is happening right now in our surroundings. So this is, we are Europe here. This is United States, and this is, if this is geopotential height, this is what we think is a Rossby wave. It's wavy behavior. The flow, as you can see, the flow goes along, not always perfectly, but of course there's convergence because we need to create cyclones and anticyclones. But essentially the flow goes around here. And then let's see what's happening, because I want to suggest that this wave pattern is actually quite stationary if we go on in time. You see, these waves seem to have just a wave number which is not moving very much with the mean flow, but it turns out to be a wave number that is just happens to be more or less stationary. We will derive next lecture what kind of what wave numbers that should be. There's just one wave number given the flow conditions and the latitude that can be stationary. But as you can see, not much is happening. It's just standing there. It's not advected over. For example, this wave in the Atlantic here, you would expect maybe if it was a short wave. You see, this wave is short wave, is moving, right, with the mean flow. And there are other features that may be moving, but it seems the large-scale patterns are quite stationary. They do not move. It's getting too slow.
This is the pressure at surface.
This could be the surface pressure. It's not a perfect, yes. It's not perfect. It would be better to show the 500 hectopascal geopotential height because the surface pressure may be too much.
So here we can expect also heating effect.
Yes, because we also see a strong convergence, for example, at the surface here. But yeah, but okay. I didn't know how to get the geopotential height. But as you can see, we are now a few days ahead, and the wave pattern has remained more or less stationary. It's not moving. It's just sitting there. No, but extremely boring. But sometimes we can be in situations that are like this, and sometimes the waves can be moving in this or that direction. Anyway, this is just an example. Of a possible, right now going on, a possible cancellation between these two terms. Of course, as you mentioned, there are probably many other processes that try to modify these waves. But it seems right now we are wave numbers dominating that are pretty much cancelling these two terms, so the waves are more or less stationary. Yes, so that the exercises, they should be straightforward this time. Actually, they're quite interesting. Here we give a geopotential height distribution, and you should calculate in the end what kind of vertical velocity field is consistent with this using the vorticity equation. And here's also an interesting equation. So I can tell you these could be potentially relevant for the final exam, because this is a nice thing of inserting numbers, doing some calculations. So these type of exercises are maybe more relevant. Okay. We have deserved our lunch now.